All right, so X's don't repeat, Y's don't repeat if you're 1 to 1. Neither of those repeat. All right, so let's talk about what special property there are for 1 to 1 functions. 1 to 1 functions have inverse functions. And that's the special property that we're going to be using throughout chapter 6 is the fact that they have inverses. Okay? Inverse functions interchange. So we'll use a big word. What's another word for interchange? Switch, swap, change the sides. That's exactly right. Interchange. You swap sides. Okay? Interchange, swap sides, the domain, and range. Inverse functions, interchange, swap, the domain and range. That's very important.
The range is fixing to be the domain, and the domain is fixing to be the range.
On the inverse. That's what an inverse function does. All right, so let's look at a function, all right, and decide if it's 1 to 1, and then find its inverse. Okay, so is the function 1 to 1? If so, find the inverse. Okay. Example A. Example of A. Here's our function. We're going ahead and telling you it's a function. It's f of x. And let's do a really, really simple example first with ordered pairs. All right. So is that a 1 to 1 function? And why? Okay, we check the x's to make sure it's a function. Well, they told us it was, but we want to make sure -3, -1, 2, and 5. X's don't repeat. 6, 7, 13, -8. Y's don't repeat either. So this passes the 1 to 1 test. So it is a 1 to 1 function. So the inverse swaps the domain and the range. Which part is the domain? The x's. The range, y's. So swapping the domain and range just turns those ordered pairs around. Each one of them. Yes. 7, -1. 13, 2, -8, 5. Now, notation for inverse. F inverse of x. It's like a little -1 exponent. There, that's the inverse notation. That you read that, you don't read that f to the -1 power. You read that f inverse of x is how that's read. Okay, so finding the inverse. Really, really simple when it's ordered pairs. Equations, not as simple, but still pretty easy. So let's say, that's it, yeah. We found the inverse because it was a 1 to 1 function, so yay. Okay, so let's start with a pretty easy equation. F of x is 6x minus 7. We know that's a function because it's a slope-intercept form of a line. So that passes the vertical line test. Would that pass the horizontal line test? Yes, so that means it's what? 1 to 1, that's right. So it's 1 to 1 because it passes the vertical and the horizontal line test. So it's in slope-intercept form. We know what that looks like. It should look like a line that has a y-intercept of -7 and a slope of up 6 over 1. So it's slanted like that. That's just what we know.
What's one that don't?
We'll get to that. Okay, so let's work with one that does, and then we'll get to one that doesn't. All right, so here we go with this. How to find the inverse. F of x is the same thing as y, right? So instead of writing f of x over and over, I'm going to put a y there. So it makes the algebra a little easier. What does a inverse do? Swaps the domain with the range, right? Swaps x and y. Now solve it for y again. Divide everybody by 6. X over 6 plus 7 over 6 equals y. Convert that to inverse form. F inverse of x equals, and I'm going to write it 1/6 x plus 7 over 6. Because that's slope-intercept form, right? Makes pretty good sense that the inverse of a line would be another line. They're related that way. Well, you're swapping x and y to find the inverse, and then get y by itself. And that y, this y is the inverse. It's not really swapping x and y twice. It's swapping x and y once and then solving for y to get the inverse of what you're doing. All right, let's look at another one. A little bit more complicated problem, the kind we tend to have trouble with. All right, so here they're giving us a rational expression as a function, and we are to decide if that's 1-to-1. They tell us that it's 2x plus 1 over x minus 1, and then the x can't be 1. Why did they tell us that? Domain, yeah, domain of that thing. X minus 1 on the bottom tells us x can't be 1. Okay, that does not affect how we go about doing that. Now, here's what we want to do. We want to decide if that's 1-to-1 or not. Pretty tough to do. We can't really visualize that graph. So I would graph it with my graphing calculator. And you could do this with, we'll ask, how do you know that passes the horizontal line test on the first example? You could graph it on your graphing calculator, and that could help you.
That's what I thought about doing. And everybody's like, oh, yes, it is. I had no idea that y'all knew that.
Oh, well, they had Algebra 1 when they were in 9th grade, so they learned that there. Ooh. Sorry. You got shady there, didn't it? We should know that it has an asymptote at y equals 2, and it also has a vertical asymptote at x equals 1, because we've done rational things, right? We did a whole, chapter 5 was about that. So we should know that stuff. But maybe we don't. Maybe we need to get a little reminder here. So there's our graph. Does that pass the vertical line test? Yeah, it does. Does it pass the horizontal line test? Do these ever get completely flat? No. Remember, there's a horizontal asymptote here at y equals 2. Because it's irrational, the degrees are the same, so it's the ratio of the leading coefficients. Remember that stuff? That's there. So they never get really flat there. They just keep getting closer and closer to that. And we could decide if it crossed it or not if we wanted to. There's a vertical asymptote at 1. We know that also, or should know that also. So this passes both the vertical and the horizontal line test. Okay, so that means we can find the inverse, which is fun, right? Go ahead. What's your question? Because it doesn't touch it twice. Anywhere I place a vertical line, it only touches the graph in one spot. Anywhere I place a horizontal line, it only touches it in one spot. If it touches it twice at any place, then that would be failing, and they would not be a 1-to-1 function. So we're going to swap f of x for y. So it's the same thing. We're not going to worry about this x can't be 1 right now, because remember, we're swapping the domain and the range. We know that there's a y value that's going to be left out of the range. It's going to be positive 1, but swap x and y. So everywhere there's an x, it becomes a y. And then we've got to do some algebra to get that y back by itself. Okay. So what do we do? Multiply by the bottom there. Yeah, that's the right thing. So these cancel out, and I get 2y plus 1. And on the other side, I get xy minus x. And just distributing the x. I'm trying to get what by itself again? Y. So what needs to be on the same side? Things that have a y. Okay?
Yeah.
X times y is xy, x times 1. Distributed property. Okay? Now, so I've got this x over here, this minus x. It doesn't have a y, so I'm going to move it over there. This 2y has a y, so I'm going to move it over here. I'm going to do that all in one step. So I have xy minus 2y equals x plus 1. I added it.
Oh, okay.
Just like I showed right there.
Sorry.
Now, here's where algebra 1 comes back. Guess what? What do these have in common? So we could factor a y out, right?
Yeah.
X minus 2. Now, what's going on between y and these parentheses? The multiplying, the opposite of that would be, if we divide by x minus 2, what's going to be left by itself? That's what we want. So, f inverse of x plus 1, or x minus 2. What's our domain that we need to tell them about? X does not equal 2. So we're kind of shorthanding the domain on this part because it doesn't come up on every problem. It's really not that bad. I mean, you got a rational expression to start with. You got a rational expression at the end. We had a linear one on the previous example. We ended up with a linear one at the end that kind of makes sense if they go together. That was okay.
Probably a stupid question, but okay. So 2y plus 1. Are you not going to do like 2y squared?
Well, you can't because these are canceling each other out.
Okay, gotcha.
Before that happens,
I was wondering why.
let's look at another one. Let's do what else? G of x is equal to x squared. And then they tell us about the domain being x is greater than or equal to 0. Why? It's what? Are you sure? It would be, but what does the x is greater than or equal to 0 tell us? It's only the positive side. So it's only that half of the parabola. So then it does pass. So that's where the domain can come into play here, is that normally x squared is a parabola, and it's not 1 to 1. But because they said it's only the x's that are greater than or equal to 0 that we're graphing, it's only this half of the parabola. So it does pass the 1 to 1 test out of that. So that's what allows us to work with this problem. So it is 1 to 1. Now we got to find the inverse. Swap it. This one's quick. How do we get y by itself? Now, here's what we got to be careful of. Which side of that do we keep? The positive or the negative? Why? Why positive? All right, so yeah, what are the y values like when x is greater than or equal to 0? They're positive as well for x squared. So only the positive side of that. So the inverse g inverse of x is the positive square root of x. And then, again, x is only greater than or equal to 0. Had they turned that around and gave you g of x is equal to x squared for only x's are less than or equal to 0, does that change whether it's 1 to 1 or not? No, it's still 1 to 1, right? Because it's only half of a parabola. Either way, let me move this out of the way. We'll just make that example E, because I think it's worth it. Finding the inverse works the same way. Take the square roots. The difference is which side do you keep? Why the negative side? Yeah, because that's all negatives up here, right? So that's why I'm going to keep the negative side on that one. So g inverse of x for this one is negative square root of x. X's are less than or equal to 0. So that part's not as confusing as it seems. It's pretty straightforward on that. All right. If it gave you one at the beginning, you would. If it doesn't give you one, there are no restrictions, so you wouldn't have any restrictions at the end. They're only going to give you that domain restriction if there are any. So you won't have any if there aren't any to begin with. Okay. All right. So let's do last thing. And if we don't get this in before the bell rings, that's okay. Verifying inverses. This is where the composite functions relate to the next section. If f of x and f inverse, or let's do this, f of x and g of x are inverses. Get this last statement in, we'll finish this in the morning. F composed with g will equal plane x. G composed with f will equal plane x. That will always happen. The composition of the two together will simplify out to be x by itself. Okay, we'll do an example of this in the morning when we come in, and that'll get us an example or two of this, and that'll get us through the lesson. If you want to start working on some of that, you can do page, start on page 415, 11 through 95 is what we're looking at there. You'll get to the problems where it says verify, and we haven't seen that yet. So, but I will do a few examples of this in the morning. It won't take 10 minutes probably.